Beyond the headlines. This is World Insight.
Hello and welcome to World Insight with me, Tian Wei, our special series, Season of AI and Basic Sciences. The 2026 International Congress of Basic Science, or ICBS, opens in Beijing on the weekend with the inaugural ICBS medals honoring scientists whose breakthroughs have advanced mathematics, physics, engineering, you name it. Among them is Professor Wang Yifang, member of the Chinese Academy of Sciences. From the Daiyabe reactor neutrino experiment to the Jiangmen underground neutrino observatory, his work has driven China's rise in neutrino physics, which helps human beings to answer some of the biggest questions about the universe. Where did everything come from? Why does anything exist at all? And what the universe is really made of. Here is my report. A small crystal ball on the table of Professor Wang Yifang seems to be his most favorite item. It's a miniature of Juno's central detector. Juno, by the way, is an enormous experimental facility installed underground, 700 meters deep. It was built to detect the neutrinos, believed to be the universe's fundamental particles, whose properties, including their absolute masses, have yet to be fully understood. This is the Juno project.
This is a model and laser craft. So you see the structure of the detector, and also there's a symbol neutrino inside.
That's amazing. I thought it was a victory, no?
Well, it's a neutrino.
Oh, this is how it looks like.
Right.
700 meters down.
700 meters underground.
Yeah.
We have this detector, which is 40 meters in diameter.
One can say the Juno project is as imaginative as science fiction. And the questions that Wang and his collaborators from all over the world seek to answer are more than fascinating. Among them, what is the universe made of? Challenges to find exact answers are obvious, but there is already hard-won initial success. For example, early in June, the Juno collaboration published its first physics results in the journal Nature, reporting high-precision measurements of two neutrino oscillation parameters. That includes a difference between the squares of two neutrino masses. In simple terms, thanks to Juno, we understand neutrinos better. Neutrinos are abundant throughout the universe, but their masses are extremely small. No wonder they are nicknamed ghost particles. More than 1,000 people around the world are directly involved in the Juno project. Wang wants to honor each and every one of them.
Inside, we have our first result on the performance of the detector, signed by more than 1,000 authors. You see, everyone who have been worked on this experiment in the last 10 years have the right to sign.
All their names.
Yeah. Yes. So
co-authors.
Everyone who worked on this project in the last 10 years.
Where is yours?
Mine's it's alphabetic, so must be very late. Somewhere here. This is the way.
Cannot find yourself. Here we go.
Yeah, okay. Yes.
All right, right here. But Rome was not built in one day. The story of Juno does not happen just overnight. I try to understand deeper the secrets behind the scene and the mysteries in the universe through a chat with Professor Wang Yifang. Professor Wang, what a pleasure to see you.
Nice to meet you.
Thank you so much for hosting us in your institute.
Thanks for coming.
At this moment, there are trillions of neutrinos going through my body, right?
Yes.
That's how many there are.
The total number of neutrinos are same as the number of photons in the universe. Every cubic centimeters, there are 300 neutrinos in the whole universe.
Right.
So if neutrino has a little bit of mass, they are going to change dramatically the history of the universe and the future of the universe.
Why neutrinos matter? Well, you are in neutrino physics. Maybe you are the best person I should ask. Why does it matter?
Neutrino is a very peculiar kind of particles. So the whole world are made of only 12 particles, and we call the fermion particles. And among these 12, 3 are neutrinos. So they are very fundamental. Secondly, we know very little about neutrinos. We don't even know its mass. All the other 9 type of particles, we know very well their properties. So, of course, we still have interest, but much less. we are more interested.
Human nature.
Of course, we're more interested in unknowns. Right? So neutrinos has a lot more unknowns than any other particles in our universe.
If I ask you, would you, Professor Wang, give me a special pair of glasses? It's called neutrino special glass. Of course, it doesn't exist, but what if?
Well, you will see the whole space filled with neutrinos, and every cubic centimeter, there are 300 of them, and stay there, of course, in speed of light, floating around.
I see.
And the fact that we are able to sit here is because neutrino has a tiny mass. If neutrino is massless, the whole universe at the very beginning will be absolutely flat, uniform, without any density fluctuations. If that's the case, there will be no Milky Way, no solar system, and no galaxy, and so on. So we are not going to be sit here. So the fact that we are sitting here very much depends on exact value of neutrino mass.
So the neutrino mass is really the foundation of the universe, so to speak.
It's one of the key parameters we have to know to understand how the universe works. And that's why we try to measure it.
And today it is hosting one of the largest experiments, Juno, for example.
Yes, so now I think we are mature enough, we are able to design and build world-leading experiment. The purpose of the Juno experiment is to measure neutrino mass ordering, which is one of the fundamental questions in the field of neutrino physics. We know that neutrino has a mass, and they can oscillate from one type to another. So we know they have relative masses, but we don't know which one is heavier, which one is lighter. So these are one of the fundamental, let's say, questions we have to answer. And step by step, we should resolve all the neutrino oscillation related problems, measuring all the related parameters, and then we go step further, trying to measure neutrino absolute mass, try to know if neutrino is its antiparticles or not. So the problems are one after another, and we are just one step of it.
That's a good way to say it. The problem is just one after another, isn't it?
Right.
The curiosity is always, there.
Exactly. We still have a long way to go. I think the problems ahead of us is not just something, let's say, can be resolved in 5 years, 10 years, probably 30 years, or even 50 years. So we really had to plan for that.
40 years ago, China has joined the International Physics Projects, but many wonder why it took so long for China to once again putting much efforts into gigantic physics projects.
40 years ago, we can only go out to join others' experiment to really do the internationally advanced studies. In order to host domestically the world-leading project, you really have to have attractive physics topics. You have to have advanced technologies to be able to build attractive apparatus, and also you need to have people who are able to do this kind of research. And in addition, you need also to have industrial support that you are able to make this apparatus and produce raw materials, and being able to provide the needed all kinds of possible support. So now I think we are mature enough, we are able to design and build world-leading experiment based on the existing, let's say, technologies, people, and the scientific ideas. So the idea came out around the year of 2008, and then it took us more than 5 years to develop the idea, and then it took another 10 years to construct the experiment. And now we are actually operate this experiment. So it's a long time thinking, study, prototyping, and finally construct the experiment.
And Juno, by the way, is a gigantic project. It correlates more than a dozen subjects. How do you incorporate all of them into this gigantic project? You yourself participated from day one.
The The Juno experiment is very much like any other high-energy physics experiment. So we form a collaboration and we establish so-called bylaws. We have the rules, we have committees, we have a management structure, we have elections. So everything is organized in a way that everybody happy with the
outcome.
As a member of the collaboration, they feel they have the role in this collaboration, and his voice, his opinions being heard. On the other hand, everything is running in a coordinated way, so we can move together to accomplish what we need to.
At this moment, there are quite a number of countries' scientists participating in the same project.
So we have right now 17 countries from all over the world, more than 700 members, and we have more than 70 institutions. So we work together, and we just finished our international collaboration meeting, which is held every 6 months.
And what was the result so far?
Well, every 6 months we have this meeting. We talk about our achievements, problems, and set the goals for the next 6 months, or sometimes for the next 3-4 years. And then we work together, and then we check status after 6 months, see where are the problems and where there are, say, needed resources to be reallocated, and try to solve, if any, problems.
Where are these scientists come from?
Mostly from China, more than 50%, and then the rest of 40-ish people coming from mostly Europe, France, Germany, Italy, Russia, and other countries. And some from America and also South America. And Asia countries, we also have Pakistan and so on.
That's amazing.
Yes.
To bring all of these together, it's also quite a challenge, but also a fun project, isn't it, for you personally?
Well, first of all, we have the same goal. We share the common vision about now and also for the future. And we all attracted by the project, by the physics topics. So we all working for the same goal. So I think it's relatively easy actually for us to talk to each other and to resolve any kind of dispute.
And where does the funding come from?
Most of the funding come from the Chinese Academy of Sciences, and the foreign fundings coming from, say, the respected countries, France, Italy, Russia, Germany. They all have their funding contributions to the hardware of the experiment.
So this is really a crystallization of scientific cooperation?
High-energy physics indeed is one of the model for the international collaboration. I would say one of the best. Indeed, we put all our pocket money, all our government funding, and our time, our people to work on the same project. So it is actually a very good model of the international collaboration.
The Juno project, I understand there's underground 700 meters under the ground experiments going on. Wow, that is really gorgeous.
Well, the neutrino experiment generally required to be in an environment which is very clean. Clean means radioactively. So you have to shield backgrounds from cosmic rays, shield backgrounds from rocks, and so on. So the detector has to be built underground with a large volume of water to shield all possible backgrounds. So that's why we built this detector 700 meters. Why not deeper? Because we are limited by funding. So that's all what we can.
But 700 meters is really already very impressive.
But comparing to other underground experiments, dark matter searches and other neutrino experiments, we are relatively shallow. So
I see.
I think many of them go, say, 1,500 meters or even 2,000 meters.
That's your dream?
Of course.
Next stage?
Well, it's probably not impossible.
How is this Juno project different from the Daya Bay project? Most of people are aware of the stories related to Daya Bay as well. Tell us more about these two different projects.
On the one hand, Juno is a continuation of Daya Bay from point of people, experience, and also the physics motivation to some extent. But on the other hand, indeed, if you look at the detail, Juno experiment is actually doing something very different. Juno trying to measure neutrino mass ordering, but Diabase trying to measure neutrino mixing angle theta 1, 3. So they are pretty different. But we share a lot of things in common, like the technologies.
Artificial intelligence now has become a tool for scientists, AI for science, as we know. How much do you think it can be of support of your latest research?
Well, in our field, AI, more particular, the neural network has been used for more than 30 years. It's not something new. We are very much familiar with. Of course, technology has been improved, and the neural network is different from what we have been used 30 years ago. But fundamentally, it's the same. It's a tool which we are familiar with. It can help us to improve the performance of the detector, performance of the software, and also nowadays with with new AI capabilities, we can even generate our software code. We can generate the figures, the text, and even the tech note using the AI. So it's a very efficient tool, and we have been using it in a very extensive way. Our efficiency has been improved dramatically, but it's not going to change fundamentally our thinking. So still, the physics, science is still driven by human.
How AI can be better used by people in the specific area of research you are working on?
Traditionally, we use AI for pattern recognition, and now we can use AI to generate code, generate text, and in the future, what can be used, we don't know, but we think we may try to use AI with physics knowledge. So we input the non-physics laws so that the AI can do some, say, analysis using existing physics knowledge and generate some outcomes of, I don't know, data analysis or draw some conclusions from the input.
Where does the imagination, the creativity really comes from in the physics world like yours?
Well, I think there's no rules, no laws, and no formula. It's just sometimes a thinking, discussion. You may end up with 10, 20 different topics, and then you have to choose. Sometimes by accident, sometimes by analysis of comparisons and so on. So it's hard to say, but of course, everyone have their own different taste, and someone prefer this one, somebody prefers another one, but there's no way you can tell beforehand. So sometimes it's...
so for you, it's more imagination or analysis?
I think both. So of course, before we go on a particular direction, you have to have analysis of the possibilities, experience technologies, and the landscape of the world, and see whether it's important enough. I think a very important aspect is that you have to really believe this is important. So there are people choose less important topic, which is slightly easier, and you can get money easier, and you can get your whatever publication easier. But some people take the risk and choose a difficult one. Right. So in the end, it's personal taste, the choice. You could easily fail if you choose a difficult one.
What do you mean? In the public eyes?
In scientific or technological sense, I mean, you choose a difficult one, you may fail because it's too hard to achieve what you designed for, and you have difficulties, and the specification could not be met, and so on.
Do you think difficult ones can attract more peer support, or the other way around, easier ones?
Hard to tell. I mean, there are people who prefer difficult tasks. You could convince them easily, but there are people who could come say that this is too difficult, you cannot achieve it, and they will veto it. So it's really, you had to take chances sometimes.
Basic science research. We see China has been putting tremendous emphasis on it. China is the country that stands out in trying to support basic science among all the other countries. At this moment, what does that mean to you?
I think it's hard to say. In general, support to basic science in China is escalated quite a bit in the past and also even in the current moment. Support to basic science in other countries in the world had been in a difficult period, I would say. So I think comparatively we are in a very good shape. But on the other hand, exactly to which project, to what field, and to what extent of the basics you're talking about is different, because there are people talking about useful basic science. Well, you have to find applications before you start this research, or you have to have some promise for the future possible applications. And there are research, in particular, our area is pure basic science. So you may find some a byproduct in the process, but really the fundamental motivation is for science. And this kind of research are somehow always had difficult time often, so even now.
So what is your aspiration?
Everywhere in the world had this kind of problems, so we just try to do our best, do our best work to show that the investment from taxpayers are actually was
well justified.
That was the amount of money people have been paid or government have been paid, and secondly we try to explain what we do and try to convince people this is interesting. I think China is a large country, should have proportionally contributions to the basic science to the humankind. So always under contribution, the under level of contributions is not good thing for the long run of the country and the people, the Chinese people.
What do you think about the national support, financial support for the basic sciences in the world?
I think, generally speaking, the economy of the world is not in a very good shape, and every country and the enormous pressure, complications, difficulties. So when you see this kind of need of urgency, of course, you try to put off the long-term needs and try to solve the current problems.
Is it the time for China to step forward and shouldering more responsibilities in basic science research?
Absolutely. I think this is a good moment. Comparatively, Chinese economy is one of the best in the world, and there are possibilities indeed to attract people from other countries when they are experiencing difficulties, and also invest more because others had, difficulties to invest. So you comparatively say you can take the advantages of this situation, and indeed this could help us to have a great leap in the basic science.
We're seeing the society ever more increasingly interested in basic science. Even for the kids, their curiosity about basic science development is amazing these days. But at the same time, the business world, even willing to invest into research in basic sciences, which might not necessarily gonna produce immediate applications. What do you think about these trends? Are they enough? Are we seeing a paradigm change or just atmospheric change?
I would say there are some changes. There are more people interested in science. That's because people get wealthy and they are interested to do something more useful to the humankind. Of course, the tradition in China on this kind of private support to science are very thin, and we still have a long way to go. Compared to, say, developed countries like the United States, private contributions to science are still very, very small.
How can you tell others what we are doing really matters?
We need to have contribution to the human civilization. And China's contribution in the last, let's say, few hundred years were very limited. And if you look at textbook, they are basically all foreign names. So China has to be, let's say, more advanced in basic science, at least in the next generations of kids, they could find some Chinese names on their textbook. So that's all what we need to do to have some, say, achievement in the basic science. It takes time, probably not tomorrow, but I think we have seen the trend, and we should just continue, and if possible, escalate more support on the basic science. If we can continue like this for, let's say, stably for 200 years, 300 years, the situation will be different.
That's my latest conversation with the leading neutrino physics of the world. And that is all the time we have for today and our series of AI and basic sciences. If you want to know more, search for World Insight, check out our YouTube channel, follow us on X and Facebook. I'm Tian Wei. Thanks for being with me.